Today, I'd like to talk about the theoretical foundation of learning finite state automata. So, this is the content of today's talk. At first, I would like to give several preliminaries, which I told you last week, but maybe you have to remember them again. So I will give several definitions about the formal languages and the finite state automata. And then I give a very simple generate and test algorithm for learning finite state automata. But this is too primitive and too simple, so I give another type of learning algorithm. For the preparation of the another type of algorithm, at first I will give about the prefix tree automata. And then we give generalization by merging states of prefix tree automata. And then I give more deep discussion on mathematical manner. Is that okay? So, at first, please remember about the strings. Let sigma be a finite set of symbols, just like A, B, or in the DNA case, ATCG. Is very primitive symbols, and we cannot divide it to into them more. So, such a symbol, we assume that such a finite set of symbols and call the alphabet. And this expression, sigma asterisk, is a set of all finite strings consisting of the symbols in sigma. And in this sigma asterisk, we allow an empty string, which is denoted by epsilon, round epsilon. And sometimes I use the sigma plus, which is obtained by removing the empty string from sigma asterisk. Okay? For example, let's assume that the alphabet consists of only A and B. Then the list of elements of the sigma asterisk, which is the strings consisting of A and B, is starting with epsilon, empty string, and then A, B, AA, AB, BA, BB, AA, BB, above. And in such case of bioinformatics, the alphabet ATCZ is more popular than such a and B. And in such a case, we have more and more strings in the set sigma asterisk. Okay? And mathematically, a formal language L on sigma is a subset of sigma asterisk, which means that a formal language is just a set of strings. And these are examples of formal languages. This language, L1, which I mean that strings which start with A and end with B. And the examples of the elements are AB, AB, ABB, AB, ABBB, blah, blah, blah. And another language, L2, is that the string which contains an even number of A's. In such the examples of elements in this language is epsilon, AA, AB, AB, and blah, blah. Is that okay? So, and to represent such a set of strings, we introduce a finite state automata. Finite state automata consists of several states inside and some transitions from state to state according to the symbol which the machine is looking at. Okay? And maybe all of you know about the finite state automata very well, so I would like to skip the precise explanation of this finite state automata. And in my lecture, the initial state, the state where the machine is just before the reading the first symbol, is denoted with Q of 0, and the final state is represented with double circle. And the machine accepts this string just after the state is in some finite state, just after all of the symbols are red. Okay? And in this finite state automaton represents language L of M, just like this one. And this means that all of the language elements in this language is accepted by this finite state automata, and other strings outside of this language cannot be accepted by this automata. Mathematical definition of finite state automaton is provided with this type of tuples, where sigma is the alphabet and Q is a set of states, and delta is a transition function which represents a transition table. And Q0 is the initial state, and F is a set of finite state. And I mentioned here that the finite state automata is sometimes represented by with a table, where each row corresponds to the states in the finite state automaton, and each column corresponds to the symbols in the alphabet. And this element shows that when this machine locates in state Q0 and read a symbol A, then the next state must be Q1, and so on. Okay? Do you understand? Okay. And this representation is now, today, very important for the mathematical discussion of finite state automaton. Okay? Then now we turn into the machine learning problem. Assume that we have provided two sets of positive examples and a set of negative examples, and both of these are set of strings. Then the problem is give a method to find a finite state automaton which accepts all positive examples in C and rejects all negative examples in D. How should find such a type of automaton just observing this C and D? That is a problem. Okay? And now I give a very simple solution, which, before that, I give an example. And these two are corresponding to the languages L1 and L2. But please note that this language L1 consists of an infinite number of strings. And this L2 also consists of an infinite number of strings. But all that we can provide to the learning machine is a finite number of strings. Okay. So this is a subset of the language L1, and this is a subset of the coset of D1. Okay. This is also the same. So this is a finite subset of L2. And the final task today's lecture and the next week's lecture is to find the correct finite set automaton which fits this C1 and D1. Okay. Now, I give a very simple answer to this learning problem. It is very simple. Just obey the generate and test strategy. You know that generate and test in artificial intelligence. This is the answer. At first, we assume that we have a method to generate a new automaton. You know that we have an infinite number of automatons for a fixed alphabet. The number of finite set is infinite. So at first, we have to assume such a new automaton. Then the algorithm works like this. Let be the input data, x1 to xn. So this input data is a mixture of C and D. So the input data is the union either C or D. Okay. Then initialize M as some automaton, which you write. And generate and test is very simple. At first, generate one automaton and test that the automaton is consistent to the positive examples and negative examples. And the automaton is not consistent to the examples. Then we throw away the automaton. Yeah, which the consistent means that if xn is in the positive example, but the current automaton cannot accept the example, then we have to throw away the automaton. Otherwise, if the example in the negative example, but the current automaton accepts the example, then we have to throw away the automaton. And if such an automaton is found for any elements of the input data, we have to revise, get a new automaton with the method we are assuming here. At first, we assume that we get a new method, just like programming language, the function called new. And if the automaton is consistent with all of the examples, then we are very lucky that this is the answer. This means that the automaton accepts all of the positive examples and rejects the negative examples. Very simple. But there are next point, milestone is what is this method. Here, at first I give a very simple method, and then next I will give a more complicated method. The simple method is just enumerate all finite set automata. Do you know enumeration? Enumerate means that we generate one automaton by one automaton by some algorithm. So I say that the enumeration is effective. You know that this English word effective means there exists an algorithm to generate another one. And unfortunately, the number of finite state automaton is infinite. So this is a perpetual process. But the mechanism exists, which generates automaton one by one. So such a method is called effective enumeration automaton. And such a method exists, and you can program the method in computers because every automaton can be represented with this transition table. So here is just gives a simple example. We will start with the automaton with only one state. Then the candidates are only two. The first candidate, this automaton, and this is represented with this table. Here we have another column F, which represents the state is in the final state or not. And so if there is no symbol here, mark here, then this state Q0 is not in the final state. And we have a mark in this column, this area, then the state is in the final state. Okay? So we have only two automata consisting of only one state. That's all. Then the next question. How many automata exist consisting of only two states? How do you enumerate them? I give the answer. This is one example, several examples. For example, we assume that the table here, then we are two choices. Which states are in the final state? If both are in final state, it is clearly same as this automata. So there is nothing to do. So we need to elaborate such one. So we have two choices. Also, in such a case, we have two choices. So the remaining problem is how to enumerate this square matrix. In the case, we are not afraid of the duplication or equivalent type of finite state automaton. Just giving the enumeration method only, we have such a matrix. 2 times 2 times 2 times 2 matrix. Okay? Oh, you perfectly understand. So the number of finite state automata consisting of 2 states is 2 times 2 times 2 times 2. And for each matrix, we have 2 types here for indicating the finite states. So we have 2. Is it many or not so many? I don't know. Of course, in the enumeration, we have a so-called meaningless automaton or meaningless table, but we are not afraid such candidates is generated by such enumeration. All that we have to do is we never miss any automaton consisting to the positive data and the negative data. Then next, we turn into the finite state automaton with with 3 states. Then you can also, at first, list all matrices like this. And then enumerate all the possibility of finite states, set of finite states. Then we will complete the enumeration of automaton with 3 states. Then the enumeration of the finite state automata is just like this: M1 and M0 and M1. This is corresponds to the this machine corresponds to the empty set, and this machine corresponds to the all of the strings of these 2 enumerations. And then we list up these 2 to the 5th powers automaton consisting of just 2 states from M3 to here. We have 2 to the 5th powers automaton here. The order is just you like. And then next, automaton consists of 3 states. In such a manner, we have a complete enumeration of finite state automata. Of course, the automaton consists of, for example, 100 states. I don't know how many times we need to reach such a very complicated finite state automaton, but this list enumeration method is complete. This is very simple. You understand? And the next milestone is that this algorithm correctly works, this means that this algorithm eventually terminates and output an automaton which consistent with the positive examples and negative examples. But this is also established because this list is complete and the set of positive data is finite. Then there is at least one finite automaton which accepts just the set C1 and rejects all of other strings. I will show the such automaton later and analyze it more deeply. So, but all of you know about the theory of formal languages and finite set automaton. So please refer the textbook of finite set automaton. Then it is said that for any finite set of strings, there exists one finite set automaton which accepts the language. Okay? So the algorithm terminates. And fortunately, the algorithm gives the smallest automaton, which is consistent of positive and negative examples. This is very good property because sometimes in machine learning, simple result is better than more complex results. So in the sense of number of states, the algorithm generates from smaller one to larger one. So we get the smallest automaton consistent with the positive and negative examples. So it is very simple, but we have a good advantage. Okay. Next, but this is somewhat too simple, and someone feels it is not learning, but just an application of generate and test of the strategy. So we turn into more complicated method of learning. Okay, so we turn into the prefix tree automaton. Do you have any questions about the first simple algorithm? Okay, then we give a prefix tree automaton. So I said that for any set of positive examples, there exists a finite set automaton which accepts just the positive example elements of positive example. Such an automaton is called prefix tree automaton. Prefix tree means that yeah, like this. This is examples of positive examples. Then this automaton is represented just like a tree. So just like and this tree is consisting like this. From starting with this Q0, and if the first symbol is A, then we go to this one, this state. And next, the symbols B then go to this state, and this is the final state. And the next string here, AAB, is starting with A, and the next state is here. And the next symbol A, which is a difference from B, which is a first, in the first symbol string. So we have a branch here. And this is the state for this symbol, this string. And then the next symbol is B, so we go to this state. This is the final state. In the same manner, for each strings in the positive examples, we generate a path from the root, the initial state, to the leaf corresponding to the end of each strings. Then we get a tree. And all leaves of the trees are final states. This is called prefix tree. So, and this automaton accepts only the elements in the positive examples and rejects all of the strings outside of these positive examples. And please note that this automaton does not satisfy the mathematical definition because, for example, we have no transition from here when we read the first symbol B. There's no transition for B, just like these strings. But we can assume that a new state, hidden state, just like Q infinite, like this, and all of the missing arc from each state must be connected to the hidden state. And just once the automata go into the hidden state, the automaton cannot accept any strings. Such a state is called a dead state. But to representing a dead state is somewhat complicated and avoiding our discussion later. So I omit such a dead state. But please add in your minds that there is a dead state here, like this here, for all of the states missing arcs. Okay? Then, next question is, so mathematically, we modify the final definition of final state automata just like the transition is not a total function but partial function. Partial function means several pairs of inputs. The value is not defined. In the table representation, there is some holes or missing elements in the table. Then the next question is, of course, this is a very good answer to the learning problem. The first problem to provide a method which accepts all positive examples, provide a method to generate an automaton which accepts all of the elements in the positive examples and rejects all of the strings in the negative examples. So this is a perfect answer. But maybe no one of you are not satisfied with this answer. Why? First, this answer, the prefix tree automaton, overfits C. Overfits means just fits the positive examples. But the positive example is a partial observation of hidden positive examples, total set. But just fitting such a partial representation, we cannot regard such an answer as a result of learning. So, if the tree automaton must be revised, if new examples are added to C, and each in such a case often happen in practical situation. And more intuitively, or more feeling point, intuitive explanation is the prefix tree automata T does not generalize C. When we have the terminology learning, many people consider that it is an activity of making general guesses from examples. But there is no generalization here. So, and in other words, for the negative example, it is somewhat overgeneralization, because the automaton rejects all of the strings outside of the positive examples. So, then we try to generalize the prefix tree automaton by merging states. So, the prefix tree can be transformed into more general automaton by merging several states into one state. Okay, so I will give a very simple, I will illustrate the method with very simple example. That means that the positive examples are only two, ABB and BAB. And we have only one negative example of AB. Then I will try to generalize these states. At first, I will try to two states. Yeah, these two are the nearest states from the initial states. I will choose this one. And I try to merge these two states into one. Then we get this automaton. But this automaton is more general than this one. Why? You know this, that the first automaton in this string accepts just A, B, B. But we merge these two states into one, and we get here, and then this automaton can accept AABB, AAABB, and BB. Just skip the A or several. So we can move this circle as you like. So this automaton is more general than this one. But unfortunately, after this merging two states, we have some contradiction as an automaton, because we have two arrows from this state labeled with B. So next, we merge these two states to remove the contradiction. Then we get this one. Sorry, we omitted this. A and B. This is A. We need here A. Then we get this automaton. And then we choose the next second state nearest to the initial state, this one. And try to merge these two states into one. Then we get this state here. But we have also contradiction on this state, because we have two arrows labeled with A, like this, these two. So we have to merge these two into one for removing the contradiction. So we get this finite state automaton. And then we also have three edge arrows here for making a contradiction. So we have all these states into one. But unfortunately, this automaton accepts negative examples. Then what is wrong? Until this situation, it works well. But we have several candidates or pairs to merge states. I chose that the nearest state to the initial state, but I don't have any strategy how to choose one. So another choice is to choose these two. Then we get this automaton, but we have some contradiction here. And then to merge the contradictory situation, and we get here with this automaton. And also, we get these two into one, and then we get, finally, eventually, we get this finite state automaton. And this automaton accepts C, but rejects this one. So this is a more compact automaton, more compact than this prefix tree automaton. Do you understand? And we cannot merge these two, because if we merge into one, then the automaton will accept these negative examples. So we stop here. This is one reasonable algorithm to generate an automaton which consistent with positive and negative examples, and contains mechanism of generalization as a merging two states. Okay. So now I will give some more mathematical discussion. At first, please note that we have two types of merging two states. One merge is like this, merge two states for making a general automata. The another type of merge we signed with this red one is to remove the contradiction as a finite state automata. So the strategy of making generation is first choose two states for generalization and then remove the contradictory couple of states. And this algorithm works well. Okay, so now we give several definitions and results in mathematical manner. Okay, at first I have to explain that why the automaton is called prefix tree automaton. And what is a prefix? A prefix of a string S is a substring of the at the beginning of the initial string. So, for example, the prefix of AAB is epsilon, A, AA, and AAB. And for the convenience of representation, we give a P of S, which consists of all of the prefixes of strings in the set S. So the prefix set of this set, consisting of AB and AAB, is epsilon, AA, AB, AB is here, and AAB. Okay? Then, prefix tree the definition of prefix tree automaton is very simple. The automaton is defined as like this. The set of states are indexed with a prefix of some words in S. And the final state is the state indexed with the strings S itself. The key point is that all of the states in a prefix tree automata is indexed with this is a epsilon indexed with a prefix of words. So this state is indexed with Q epsilon, and next QA, QAB, and QBA. So following this notation, this state is indexed with epsilon. This is the initial state. And this state is indexed with A, because prefix of A corresponds to this state. And this state is indexed with AB, because this corresponds to the prefix AB. And ABB is in this, this set, so ABB is a finite state. So we have a double circle here. And this state is indexed with B, because B is an index of B. Prefix here, and BA is a prefix here, and BAB is in this set. So this is very convenient for representing the merge of two states. So merging two states here is generate a sets of prefixes like this. So, and I missed how to define the transition function here, but maybe you can easily construct the transition function. So I put this in homework. It's very lucky. Missing here. Then, so merging is, merge states are called partition in the theory of generalization of automata. And partition is collection of subsets of states where every BI is non-empty set of states, and all BI and BJ are disjoint. And if we combine all of these B1 to Bn, we get the whole offset Q here. So every BI is called a block of pi. And so a block represents a state obtained by merging the states Q1 and Q2 into one. So merging is making a subset of states, and in other words, every state is indexed with prefix. So merging is making a subset of prefix. Okay, so merge two states is making a union of two blocks. Okay, and a partition is consistent. This means that if some states merge into BI, transit to another state with symbol C, and different state Q in BI transit to another state, but these two states are in the same block, then we have this consistent, this partition consistent. Inconsistent means that these two arrows are to the different partitions, different blocks. Such a situation is inconsistent. But intuitive explanation is just like here. So these two are inconsistent because we have two different blocks. Yeah, of course, one state, consisting one state is, of course, one block. So these, in such a case, this automaton is, this partition is inconsistent. So we have to merge these two into one to removing the inconsistency. Okay. Then, if the partition is consistent, we can define partition function, partial function here, transition function. And so we get finite state automaton. This is a mathematical definition of the my intuitive explanation of this merging process. So this is not the state now, but it is a block called block in my mathematical definition. This block consists of only one state. And this block consists of two states, epsilon and a. Yeah, epsilon is an index of states, and a is also index of state. Now, we get the so-called quotient automata, quotient by this partition here, which can easily define like this. I'm preparing this one, these notations and mathematical definitions. We get the, we present the whole of the algorithm, merging algorithm, generalization algorithm, which is called RPNI, regular positive negative inference algorithm, provided in 1902, 20 years ago. And inputs are a set of positive examples and negative examples. And at first, we make a list of prefix in strings in C. And how to make this list is very important, but I will discuss later. And then next step is we merge two blocks into one according to the appearance of this list. Okay. Choose two prefix here and try to merge them into one. And if the obtained automaton have several inconsistencies, then we also have tried to merge the two states to remove the inconsistency. And finally, the obtained checks whether or not the obtained automaton accepts any elements in negative example. And if it accepts at least one negative example, we must throw away the choice of merge. And according to this algorithm, I made this illustrating example. And in this illustrating example, I use order to make the list of prefix. The prefix is, the order is the lengthwise lexicographic order. Lengthwise means that S is smaller or larger than T if the length of S is shorter than T, or if the length is same. S is earlier than T in the lexicographic order. Lexicographic means that it appears in the dictionary. So, at first, we choose these two because the ordering is, I'm just here. The list is like this. This is a list. Shorter is later, earlier, and lexicographically earlier is earlier. Then, at first, choose these two. Here, and removing the contradiction. The next, choose these two. Here, but try after merging these two, we have to remove the contradiction, and we get some automaton which accept negative examples. I think it is correct. Here, epsilon b. So I abandon the merging these two states, and the next candidate is this one and this one. This means that this one, B and BA. Here, B and BA. Because all these are already merged. Okay. This algorithm, just like works on this. And I give the most important advantage of this algorithm. The key point is that this algorithm has a very important property in modern analysis of machine learning algorithm, because this algorithm has only two groups for selecting states. So the total amount of running time is bounded in polynomial. Because only we have two groups here. So, and to observe this, how many states here is represented with the length of total length of positive examples. Because every state corresponds to the prefix. So the total amount of the number of states is bounded by the total length of positive examples. So the running time is bounded by polynomial. Of course, we need some other process of choosing two states into one, but of course that choice is also on the combination of two states, so it is also bounded in polynomial. So this is so-called polynomial algorithm for providing conjecture or providing results of automata. The first simple generate and test algorithm is very simple. But the bad point is it has a very, very long enumeration queue for candidates, enumeration list of candidates. And in the worst case, we need more than exponential time to get the correct candidates, correct automaton. But in this algorithm, we have get in polynomial time of the total size of positive examples. But this algorithm has also a fault. This algorithm deeply depends on how to make this list. Now I explained the example here. This is the same situation that another situation that we have positive example A, B, A, B, B, A, B, B, B. And we have also a lot of negative example here. And assume that we make this list in the inverse order, just like longer is earlier, and lexicographically later is earlier. Then what happens? At first, we have to merge these two because these two are longest one. So we get this one. And next, we have to merge these two, the latest two. But we cannot this one. We cannot merge these two states, because this automaton accepts A, B. Something wrong? Sorry. This works well, but the next step we will fail to merge these two. Maybe the algorithm output this automaton. And maybe you notice that this positive set is a truncation of repetition of A only or B only. So this is a very good automaton to represent that language. But if we lack several negative examples like this, then the algorithm output this automaton, because the negative example is too short. So we cannot avoid the merge, any merge. So we get this automaton, which contradicts our conjecture. This means that if we get more and more negative examples, the algorithm revises the automaton, just accept new negative examples. But if we use this ordering, shorter is better, lexicographically Oria is better, then we get very natural automata here. So the activity of this algorithm deeply depend on this making this list. And next week I will give more deep analysis on this algorithm and the first algorithm on the viewpoint of estimation. And on the viewpoint of estimation, this ordering is better than the previous ordering. And now I have to explain what is estimation and something like that, but I have only 10 minutes or so, so I'll stop here today.